So going back to this, right, we just think about the hybridization. So I asked you guys if you have an sp orbital, right, in our carbon, we still have those p orbitals left over, right, and they're going to come back up. So we're going to take a look now going forward. So I will ask you this: how many sp3 atoms, how many sp3 hybridized atoms are in this intermediate? So how many sp3 atoms do you see here? Any idea, or you have no idea? I think it's sp3, right? Okay, Beyonce says 3. Anyone have any other guesses? Matthew says 2. Melissa says 6. Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 possible atoms. Hydrogens can't be hybridized anything else besides 1s. So it's going to be these 9 atoms we have. So real quick, and this is something I think you were talking about, Melissa. Do you know what atom is right here at this juncture?
Carbon, and it has 2 hydrogen bonds.
Correct. I think that was in that video I made, right?
I haven't had a chance to watch that video, but like Duas went over this already.
You're dead to me.
I'm sorry, it's too busy.
So sp3, right? How many unique things was sp? What was our example? The first one we started with that was sp3.
Methane.
Right? And how many different things was it connected to?
4.
4. How many different things is this nitrogen connected to?
2.
1.
Oh wait, is there not hydrogen in the nitrogen and next to the nitrogen? Like,
nope, because remember nitrogen only likes 3 bonds in a lone pair, right?
Oh, that's right, yeah.
So is this sp3 anyway? It's only connected to one thing, right?
No, it's not sp3.
What about this carbon?
That's not sp3 either.
Yep. What about this carbon?
That one is sp3.
That is correct. What about this carbon?
That one is sp3.
That's correct. And those are the only 2.
Is there not another? Oh, never mind.
Yep, that's because this carbon has a double bond, so it's sp2. This nitrogen is going to be sp2. This right here is sp2 because it's only connected to, these 2 things and a hydrogen, but it has a plus charge. This carbon is connected to 3 things. It's sp2. This oxygen is double bonded to one thing, but it has 2 lone pairs, so it is also sp2. So only these carbons here, here, and here. So if a carbon only has single bonds, it will be sp3. If a nitrogen or oxygen only has single bonds, it'll be sp3. Once you start adding double bonds, triple bonds, you have like a plus charge because you're missing a bond, then it's no longer going to be that sp3 hybridized. Does that make sense? Yes, it does, Dr. V. Oh, okay, good. I was worried. All right. So now when we think about here, this carbon, right? This carbon is connected to 1, 2, 3. It has 3 things. So then therefore, we're going to need to hybridize 3 of the orbitals, right? We're going to take an S and 2 of the P's and we get sp2. So then I'll ask Melissa, what is this p orbital doing that's left behind? What's it doing now? It's not hybridized and it's just chilling out there, but what's it doing?
Honestly, I'm not sure.
Okay, so how many things is this carbon connected to?
3.
All right, so we could say that this is the hydrogen, this is this hydrogen, and then this one is this carbon, right?
Yeah.
And so we said that every bond, whether it's single, double, or triple, always has a sigma bond, right?
Yes.
What is this other bond, though? That is a what type of bond?
A pi bond.
A pi bond, which comes from what type of orbital that might be left over? P.
P?
Our leftover p orbital, right? Because we took these 2 p orbitals and the s to form our hybrid, and we had this leftover 2 p orbital. That 2 p orbital is what makes up the pi bond. Does that make sense?
Yeah.
Are you sure?
Yeah, that makes sense a little bit more. So is it just so there's a hybridized p orbital that forms the pi bond from the double bond. So it's actually 4 bonds, but it's only 3.
It's only connected to 3 things.
Yeah, it's only connected to 3 things. Okay.
How are you guys feeling with that in general? Does that make sense where the pi bond is coming from, that leftover p orbital? Are the rest of you mooks feeling okay? All right. For those of you, Alyssa said she's coming. Oh, good. Okay. So for those of you who don't know, this is a funny story. Beyonce, I call, most people, I think some other, other people call her Bay. One day in class, I called her that. And I said, hey, Bay. And the look I got from the students around her, because they thought I was saying BAE, oh, those were not happy eyes from students. They were like, who is this? What is happening here? I thought it was funny. Made me laugh. Someone did ask me afterwards, and I said, no, her name's Beyonce, and I call her Bay for short. And they're like, oh. And one girl who will go unnamed said, I thought you were just a dirty old man. And I'm like, no. I'm a weird old man, but not a dirty old man. So, fun fact or unfun fact. So, I wanted to look at them and say, I think Bay could do a lot better. Let's give her a little bit of credit. She's not finding some poor old professor. She could do better. So now, are you guys okay with this idea now of we take our hybridized orbitals for every unique thing we're connected to, whether it's a bond or a lone pair, right? Before the world collapsed. Yeah, I would have been at NAU had the world not collapsed, because I would have got hired full time. So such is life. That's all right. So now we can see here that we have these sp2 hybridized orbitals, right? And now they're more like that 120 degrees. But then we have these p orbitals left over. So that p orbital is what's going to make our bond. So now, how many sp2 hybridized atoms do you see? How many sp2 hybridized atoms do you see here? Basis 2, Matt says 5. Like 152 more than 151, dead to me. Just like Melissa's dead to me. The answer is 5. So I know that these two are sp3, right? That still hasn't changed. How many things is this carbon connected to? 2. So is it sp or sp2? This is sp, and so is this nitrogen, because it's the lone pair in the bond. So this is sp. So sp, sp, sp3, sp3, 1, 2, 3, sp2. 1, and then the 2 lone pairs, sp2, 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 sp2. So if you have one double bond, you're most likely going to be sp2. Does that make sense? So basically 1, 2, 3, 4, 5. Of course I'm right. So you have to ask that. This is just the idea. All right. You cannot forget about the implied hydrogen, right? You have to start recognizing it. I would say until you get used to it, it might be useful for you to draw them out just so that you're knowing that they're there. Eventually they will become second nature, or you always think about it. All right, so that's that. So now, and finally, what about carbon atoms with only 2 electron groups, right? So this is our last thing. So now we can think about this. This is acetylene, and so that carbon only has this, so it only needs 2 hybrid orbitals. And so we're going to take one S and a P, right? And so now we're going to form an sp hybridized orbital. So Melissa, coming back to you. This carbon here, right? It's a sigma bond to the right and a sigma bond to the left. What are these 2 types of bonds?
Pi bonds.
And how many do I have?
2.
Right? So how many p orbitals did I have left over?
2.
2. Does that make sense?
Yes.
Yep. So for everything I'm connected to, unique thing, every lone pair, every atom, that takes a sigma bond, a sigma orbital, right? But once I start putting double and triple, that's going to use my leftover pi bonds, right? And that's it. So now this is our sp orbital. This is what they look like when they overlap. This is an sp hybridization. And so you can see now it's a 50-50 mix. It looks a little bit more like an S now. And this is it. All right. So this is our basic idea. So if I have 4 electron groups, How many orbitals do I need for my central atom? 4.
4.
And then this is going to be what hybridization, or which I'm going to take a 2s and then my 2 p's together, and then I'll get sp3, right? I'll get 4 of them. And actually, I'm just going to erase that 2. It's confusing. All right. And if I have 3 electron groups, right, I need 3 orbitals, so I'm going to take an s and then 2 of the p's, and then I'm going to have 3 sp2 orbitals. And then finally, if I have 2, I need 2 orbitals, so I'm going to take an s and a p, and then I'm going to get sp orbital. And I'm going to erase that 4 because that's just going to get confusing between that. So if I have 4 things I'm connected to, I need to use 4 orbitals. Therefore, I need to take an s and all my p's. I'll make sp3. If I'm connected to 3 unique things, it's sp2. If I'm connected to 2 unique things, it is sp. How are you guys with that? Does this make more sense now with the hybridized orbitals? Okay. And actually, real quick, I apologize, but I just realized I had the chat box over the thing. So real quick, just so it's not to confuse you, because these are, I'm gonna rearrange this. So we'll do this again. I'll try this again because now I can see this. So there's 2 electron groups here. I need 2 orbitals. It's going to be an s plus a p, and I'm going to get sp. There are 3 electron groups. I need 3 orbitals. Therefore, it's going to be an s plus a p plus a p. This is going to be sp2, and then I need 4. So then 4 orbitals are going to be needed. So then it's going to be s plus p plus p plus p. This is going to be sp3. All right, so that is that chart filled out correctly. Sorry about that. I just realized that was that. So this is it. This is what your hybridization is. So knowing the hybridization now, if you can predict hybridization, if you can predict what it is, this is going to tell you so many properties. What is the 3D structure? How acidic is my compound? Since some salty people, no names Melissa, we're talking about acids being so much fun. But fun fact, your hybridization will tell you something that's more acidic or less acidic. So this is something that's going to keep coming back, and it's very useful to know. All right, and this is the idea of hybrid orbitals. All right. I think that should be that. Okay. So how do we draw these, right? So basically, this right here is a weird molecule to think about. This is a carbon monoxide. And this is a weird representation, right? So what is the hybridization of that carbon in this molecule? You really only have 3 choices here. sp, that's correct, right? That carbon has a lone pair to the left, triple bond to the right. It's sp. Same thing for that oxygen. Has a triple bond to the left, lone pair to the right. So each of those atoms there are going to be sp hybridization, right? And that's it. All right. All right, Melissa, don't forget, they're going to be on YouTube if someone has time. Since someone's so too good for this, have a good night. All right. So now when we look at this, how many sp2 orbitals do you see in this picture? How many sp2 orbitals, how many sp2 atoms do you see here? 2. This carbon is sp3. This carbon is sp3. This carbon's connected to 3 things, so it's sp2. This nitrogen is connected to 3 things, so this is sp2. All right. All right. So question here. What type of molecular orbital is created by the overlap of 2 orbitals head-on? Bonding orbital? Yeah. That's basically how many things it's connected to, how many lone pairs it has, how many bonds it has, and stuff like that. That's it. Yep. And so we have the question here, and Beyonce says B, a sigma orbital. And that is correct. When we have the overlap of 2 orbitals head on, that is a sigma orbital. That is a sigma bond. U is correct. There's no such thing as a delta, right? So, and a bonding orbital, non-bonding orbital, that's constructive and deconstructive, and a pi orbital are actually next to each other. All right. So now that we're coming here, something that I want you to consider. So can you guys see my camera? Can you see me? I don't know if, or if you can just see the screen. Okay.
Hi, Anthony.
Hello. I'm going to pop out of this real quick. So real quick, something that we're talking about here. So as soon as my camera comes back on, hopefully it does. Can you see me now?
Yep.
Okay. So imagine I have a single bond. It's connected in only one thing like this, right? Can you rotate your hands? You guys see this. Can you rotate? And still keep contact with your fingers? Yeah, right? So single bonds can rotate. It is not a problem, right? You can rotate them. Now, I want you to take two fingers like this, your index finger and your middle finger, put them together, and now try to rotate your hands by keeping them touching. Don't break them apart. Can you rotate them all the way without? Nope. So once you start forming a double bond or even a triple bond, they can't rotate. Only single bonds can rotate. Double bonds cannot rotate. Triple bonds cannot rotate. Does that make sense? This idea is going to come back a little bit later to haunt you. So just that's something to know. Welcome, Melissa. It's good to see you. Isn't this how boiling points work, or did I make that up? You kind of made that up. All right, so now going back to our PowerPoint. Johan, how's it going? I'm assuming he's alive there. I miss coming into section and just being like, yo, Johan. Those were the days. All right, so going back to our PowerPoint, this is just something to keep in mind is that these rotate like that. All right. So now this next question is, how many pi bonds are in cyclohexyl 1,4-diene? How many pi bonds are there in this molecule? What do you guys got? Yep, 2. This pi bond and this pi bond, right? That's it. Every time you see that, for every double bond, there's a pi bond. If a triple bond, you have 2. All right, next up. How many sigma bonds are in this? How many sigma bonds are in this? You're all wrong. Beyonce's forgetting about something that she said she forgot before. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you guys saw the 6 carbon-carbon bonds, which is true, but you can't forget about your hydrogen bonds. So since you had 8 of them attached, for every hydrogen, that is a sigma bond. Therefore, you have 14 sigma bonds and 2 pi bonds. Does that make sense? Okay. Going on from there, clear that off. Forget about that. Just forget hydrogen exists. All right, what is the shape of a water molecule? This is from our Vesper theory. So what is the shape of a water molecule? Yep, that is correct. Its electron geometry is tetrahedral because it has 2 bonds and 2 lone pairs. But since it has 2 lone pairs, it is going to be bent. Is water a polar molecule? No, it has no polar bonds. Yes, it has polar bonds. No, it has polar bonds and polarities that cancel out. Yes, it has polar bonds and polarities that don't cancel out. What letter is correct? A, B, C, or D? Matthew says B. Beyonce says either A or C, but she hasn't specified a letter yet. So if you remember, we talked about vectors. It's like you guys are having too much fun with your acids. Tell Melissa this. I called her out again. Remember, we think about if a bond's polar, hydrogen, oxygen, right? It's not an atom attached to itself, like a carbon-carbon bond, oxygen-oxygen bond. And also, it is not carbon-hydrogen, therefore it's polar. So my dipole points towards the oxygen, as that pops up for some reason. Like this. Same thing with my this. And so if you remember, to figure out the dipole, I just draw them head to tail like that. So my overall dipole moment is this. It is a polar molecule because it has polar bonds and the polarities don't cancel out. So my answer should be D. It is polar and my polarities don't cancel out. Yes, it's polar. It has two polar bonds and those polar bonds don't cancel out. Beyonce, you should always, this is true for all of you. Water is our stereotypical polar molecule. When if you say, what's the polar molecule? Your first answer should always be water, just in case that comes up. All right, and so this case, D is going to be your correct answer. All right. What is the shape of SiO2? What is the shape of SiO2? Anyone know? Before I draw it in a few seconds. I'm going to say C, all right? We've got a bent again. Beyonce is going to say A. And so Si, silicon. Again, I don't know why it does that sometimes. Weird. Like that. And so it should be linear like this. Right, and again, you just draw out the Lewis structures and see how many lone pairs and stuff. So that's it. All right. What is the shape of, that says, hold on, SO2? What is the shape of SO2? We got C for trigonal planar. We got D for trigonal pyramidal. We got B for bent. All right, so sulfur, oxygen, each have 6 electrons. So we're gonna have 18, right? Well, I'll let you guys come with the answer. So we have 18 electrons, sulfur in the middle, oxygen, oxygen. So do. So that's 4, 8. We have 10 left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that is going to be, any idea what that molecular geometry is? Or you guys literally have no idea? Technically, this is going to be, since it has 3 things that it's connected to, right? It would be trigonal planar. But since it has 1 lone pair, it is going to be bent. I feel someone hasn't shamed you in a while, so shame on all of you. All of you. All right. All right. What's the shape of NF3? This is going to be trigonal pyramidal, just to let you guys know. All right. IMF forces, I just want to go through this quickly just because. So if you're nonpolar, what type of IMF can you have? What is the simplest IMF that every molecule has? Nope. You're on the opposite end there. Every molecule, regardless of what it is, doesn't matter if it's an atom, nonpolar molecule, polar molecule, whatever, your London dispersion, right? If it's a polar, you can do London dispersion and you can do dipole-dipole. And finally, if you can H bond, it would be London dispersion, dipole-dipole, and hydrogen bond, right? So an example of our first one would be methane. An example of the next one would be CH3F. An example of this would be H2O. So those would be examples of that. All right, so don't forget those IMFs. So London dispersion is the weakest, then dipole-dipole, then hydrogen bond. Those are examples of that. All right. Going on. So increase boiling point. What is the most important thing when it comes to boiling point? Yep. Your forces, right? So C, since that can hydrogen bond, is going to have the highest boiling point. B is polar. So then B is going to be your next highest boiling point. And then finally, the difference between D and A, if it's a straight chain versus that type of bent thing where you have different things coming off, D will have the higher boiling point. So from lowest to highest should be A to D to B to C, right? And so we think about it as our intermolecular forces. So the stronger the intermolecular forces, the higher the boiling point. All right. Increasing water solubility. Which one of these should be the most soluble in water? Which one do you guys think? A, B, C, or D? Which one of these should be the most soluble in water? Okay, we got D. Any other guesses or agree with Matthew? A is another one. So when we talked about solubility, what was the phrase I gave you guys? Something mixes with something. Like with like. So which one of those is closest to water in terms of intermolecular forces? Nope. Well, water is what type of molecule? It's a polar molecule that can do hydrogen bonding, right? So which one of these molecules can do hydrogen bonding? C. C is our water because they can do hydrogen bonding, the OH, right? Alcohols can hydrogen bond. So molecules that can do hydrogen bonding are going to want to mix with other molecules that can do hydrogen bonding, right? So since those are both doing that, they're most likely to mix, all right? And that's the idea there. So don't forget that. And this is the idea. So now, which one of these is going to be most like hexane? That's going to be D because it's very similar, right? This is 1, 2, 3, 4, 5, 6, 7. This is heptane. This is pretty much hexane. It's just one carbon longer. It has the same London dispersion. It's going to mix the same way. And this is the idea here of just thinking about, I will make a video to finish this off because I'm running out of time. But this is basically the idea here is that when we think about melting points, boiling points, when we think about commonalities, think about their intermolecular forces. The more similar they are, the more likely they're going to be soluble, right? The stronger the intermolecular force, the higher the boiling point. The bigger the molecule, the higher the boiling point. Okay, do those basic concepts make sense? Are you guys okay with that? Okay, so I think that about finishes up that first dealie. So that'll be it for the first video, and I'm gonna hit stop.